Hello everyone, I'm Dr. Aviv Yehezkel, Yehezkel co-founder and CTO, and I will present to you our work on network anomaly detection using transfer learning based on auto-encoders losses normalization, which is a key part of Yehezkel technology, and we presented last year in ACM CCS, which is one of the leading conferences on network security and AI. So I'm the co-founder and CTO of Yehezkel. We are a cybersecurity startup based in Israel and Boston. We are specifically focusing on next generation network anomaly detection. And it means for the first time, we're collecting a very small network traffic samples from whatever network size and architecture that the client has. And we developed technology that is able to learn from very small network samples, from 1%, how the 100% looks like, behaves, and predict cyber attacks long before they hit. And this is the significant difference than the existing approaches today for network detection and response, as I will touch a bit later. I have a PhD in computer science from the Technion, and my specialization is in this area. I mean network anomaly cybersecurity using machine learning, deep learning. So the challenge. Networks becoming bigger and more complex. Number of endpoints, number of devices, the network size, the size of the network traffic, the architecture, which is becoming more complex, more complicated, this messy mix, as we call it, between physical networks, switches, firewalls, like the old days, with the cloud, creating this very challenging network landscape that all the existing approaches prior to Yehezkel for network anomaly detection, which are all based on appliances, probes, sensors. It's basically boxes that are placed in the network, collecting all the traffic all the time, and analyzing this traffic and trying to understand what's going on in the network. Now, this approach was perfectly suitable like dozens of years ago when the networks were compact enough so you could really process all the packets, all the traffic. And today it's impossible. No one can do it. No one can collect, process, analyze all the traffic all the time. It's impractical, cost-wise, overhead-wise, no one can do it. And the reality without Yehezkel is to buy some appliances, to put them in strategic points in your network, which is a key challenge for itself, and leaving the majority of the network, which could be like 90% according to surveys and reports, 90% of the network is one big blind spot with no coverage, no visibility, and essentially no detection of threats, attacks, bad things that happening. And this is solved in Yehezkel with this sampling-based approach that I mentioned before, and we will discuss in this talk. Because for the first time, we collect small samples, but from the entire network. We don't leave any part of the network as a blind spot anymore. And we use this unique technology that we developed, which enabled us for the first time to learn from the samples on the full network. And this is the key technologies that we developed in Yehezkel, and in this talk I will touch upon one of these technologies. So sampling. What we see in this slide is a breakdown of 4 different data inputs technologies in network anomaly detection. Okay, it's starting with DCP dumps, collecting all the packets all the time, what I mentioned before. Of course, lots of data, lots of details on the network, which is very good, but it's just impractical. And it requires high impractical memory and processing overheads. And even for small, medium-sized networks, it's becoming impractical to process anymore. So this is the TCP dumps. Then the second technology that you see here is SNMP, which is one of the ancient protocols of networking. It's really always deployed protocol, whatever network, whatever gateways you're using. And it has very low network overhead, which is great. But from the other hand, SNMP has a very high level only volumetric information on the network, number of bits, number of packets, and that's it. It's not enough for anything relevant in today's sophisticated threat landscape, and in order to understand more challenging attacks and threats than just volumetric attacks. The third technology is IP flows. And the IP flows means summarizations of the entire traffic. It's flow summarizations, but again, it's the entire traffic, 100% of the traffic. So it's a good trade-off between SNMP and TCP dumps, but it suffers from the same issue as TCP dumps, as I just discussed it in the previous slide, because it still implies impractical overhead on processing, collecting, analyzing all these IP flows in even moderate-sized networks these days. And finally, samples. This is what we are dealing with at Cynamics. It means summarizations, but only of samples of the traffic, right? 1%, for example, of the packets are being sampled and summarized, and this is the data input that we are working with. So the advantages are that these samples are really applicable for the first time. No matter what's the network size, no matter how the network is complex or complicated, the samples can be collected from such an environment. And using our technologies, we have the ability to learn from these samples, to infer from them on the full network, which is, of course, a significant challenge for itself. And this is the key barrier that Cynamics has compared to the existing approaches. But again, it provides us the ability to cover the entire network for the first time. And of course, lower processing cost because of the samples. No privacy issue, which is becoming more and more important, as you can imagine. And it is due to the fact that the network samples are only the IP headers, only the metadata of the network, no payload, no application. The actual sensitive and private information is not part of these samples. So the client can be very, very calm that no data, no private data is ever going to be collected, processed, analyzed outside, which is, of course, very important. And finally, it's a standard built-in approach. Every kind of gateway, physical, virtual, legacy, or cloud, is supporting at least one standard sampling protocol. It's always there, and it makes the life of our clients very, very, very simple, because they don't need to prepare anything in advance. They can just get ahead, connect to Cynamics, start to send the samples, and get this full coverage and threat detection immediately afterwards. And this is a very high-level architecture of the solution. So in the left-hand side, you see this client network. And again, it doesn't matter what's the size of the network, from a very small size to the largest enterprises out there. We're working with all of them, all of the spectrum. And no matter how the network is built, what is the architecture, what is the environment, how messy between physical networks, cloud networks, everything supporting at least one of these standard sampling protocols, as I mentioned, which allows us to collect the samples into our cloud and learn from them about the full network. So the big problem, of course, how to learn from this 1% of network samples on the full network. And specifically to this talk, how to detect cyber attacks from just 1% samples, right? And of course, in any kind of application, inferring from samples is challenging, but I think that in the network security space, it's even more challenging, because the distribution of computer networks is very challenging. It's much different than uniform distribution. The majority of flows are very small, and only very small fraction of the flows of the internet traffic is what we call the elephant flows, the Google communications, the communications with the largest providers out there. So any naive estimation from this 1%, just multiply by 100 by the sampling rate, in order to grasp some understanding of the full data, will derive hundreds of error percentages and will not work. So, and this is the key behind our technologies, because it's a very challenging problem. And I will discuss now on one part of it regarding to detection of attacks. So the main contributions of this work. The problem, of course, anomaly detection in computer networks. What's new is the concept that we invented here is auto-encoder losses transfer learning, and I will touch upon it in the next slides. The method is consisting of two main steps. The first is normalization of auto-encoders losses of different clients, different networks. Normalization of the losses to domain invariant distribution, which enable us essentially to forward these normalized losses to a single global detector that is able to work on different networks, even though they are very different one from the other in the sizes, in the applications, in the top tokens, everything. And this normalization is the key invention here. The fact that we are taking the autoencoder losses, and instead of considering each losses in their own context as the classical approaches for anomaly detection based on autoencoders, and I will recall it in the next slide, I think. Instead of this, we are actually normalizing these losses of the very different networks, and the normalization takes us from very different spaces, the raw spaces of the losses, to this single space, which compares apple to apple between different clients, different networks, and provides us with this transfer learning, because the global detector is able to work on the different losses due to the normalization, and become better better expert in anomaly detection with each new network that we see, with each new attack that we simulate. And this is the key behind this approach. And of course, why we do it. So first, samples, in order to solve this challenging context of working with only sample data. And the second reason is that this normalization enables us to use the same global models on all the networks out there. Because the normalization, because the transformation from the raw spaces to the normalized space, to this domain invariant distribution, we can use eventually the same detector in a generalized way on different networks, which is very important because we don't need to train a new detector from scratch for each new client that we see. I will answer questions at the end. Okay, let's start with a quick recall on autoencoders for anomaly detection. So I believe most of you have used autoencoders in the past for anomaly detections, whether in computer networks or other domains. And it's indeed very, very easy to use, I would say, approach, and quite straightforward. And the idea here is to train autoencoder to reconstruct the input by forcing him to learn the patterns of the data such that it will be able to reconstruct the input from this loosely representation, which we're creating in this bottleneck layer, right? We are reducing the dimension of the data, and by doing so, we reducing the information that we have on the input, and forcing the autoencoder to understand patterns in the underlying data that it will be able to utilize in order to reconstruct the input, even though of this loosely information due to the bottleneck. And after we're training the autoencoder, the approach is just to look on the losses, right? To calculate the losses, the difference between the predictions and the actual input, and to detect an anomalies if this loss is too high, right? Because our assumption is that normal data, which is similar to in its characteristics to the distribution of the data that was used for the training, will be reconstructed quite well by a trained autoencoder, right? So the loss will be quite low, and from the other hand, an anomaly input, which is very different than the distribution of the training data, will derive high loss. And this is like the most straightforward approach for utilizing autoencoders for anomaly detection. Now, this approach has two main issues. The first is that we need to train from scratch an autoencoder for each and every, in our case, network, or in other applications, whatever it will be. And it means that we need to collect lots of data to train the autoencoder from scratch, to fine-tune it, to customize it, perhaps to improve it on the way in order to prevent false alarms and in order to improve its accuracy. And it means a long, tedious project until we have this autoencoder ready to go and until we start to provide beneficial insights for the client or whoever it will be. This is the first issue. Now, the second issue is that after we have done with all this long, tedious project, we need to start from scratch for the next client, for the client afterwards. We don't have any head start that we can utilize and any knowledge that we can utilize or take advantage of going from one client to another. And both of these issues are actually being addressed by our approach, because due to the normalization, as I mentioned before, and we will now discuss it, we're actually coming pre-trained. We're coming with these global models pre-trained for each and new client that we see. We don't need to train from scratch the whole models and wait for a long time before we start to provide value for the client from the one hand. And from the other hand, we can utilize knowledge from one client to another because the global models can be improved, can get better from each new client that we see. And this is exactly the motivation behind our approach. So, transfer learning of the normalized losses from one client to another. And the high-level method is the network data is our input. We are running the first autoencoder, its loss is being normalized. The normalized loss is being forwarded to a global detector model. And this global detector model is being employed on all the networks out there. So we have the single global detector, which we are utilizing for all networks. So we come pre-trained. This global detector is coming with us for each new client. Of course, it's becoming better and it's improved along the way. This is the transfer learning, the utilization of knowledge from one client to another, from one attack to another. But the key thing here is that it's a single model that is already ready to go with each new client that we see. So we don't have this long time to value as in the vanilla autoencoder approach. So we have the global detector, which detects the anomaly, yes or no. And if there is an anomaly being detected, we run an equivalent pipeline, also consisting of another autoencoder with a different architecture, a different feature base that we will discuss in a moment. And its loss is also being normalized. And then we have this global classifier, which is getting into action in order to classify the threat, the attack, what are the details, what is the attack type, etc. So the differences compared to previous work, to related work in this domain is, first, the previous work hasn't studied the sample setting like ours. It was focusing on a context where all the data is given, which, as we discussed, it's becoming impractical today. It's still, even though it's becoming impractical in the real world, it's still being the main context, the main setting in the academy prior to this work. Second, the anomaly detection was made from scratch for each new client. We trained this detection models, the autoencoder, for example, from scratch for each new client, unlike our approach, which is utilizing the same global detector for all the clients. And third, the transfer learning, the fact that we can, for the first time, we can utilize knowledge from one client to another due to this normalization. Okay, a few words about the input. So this is a flow. Okay, this is a sample flow. A flow is another name for connection. It is just 5 tuple, the source IP, the destination IP, the source port, the desk port, and the protocol. This is the 5 tuple, the most basic ID of a network communication. Of course, it has some time. Of course, it has some number of packets or a number of bits that was transmitted over this connection. And this is the most basic connection information. And I told you before that the sample protocols do not consist of the payload itself, on the application, the data itself that was sent, right? And I told it's mainly an advantage because it means that no sensitive and private information is ever leaving the client premise. So instead, we need to architect some features that will provide us insights on the network patterns. So for example, you can see here some examples of such features. For example, analyzing the flow distribution, the number of flows with 1 packet, with 2 packets, with 3 packets, etc. Or another one is the distribution of new flows. It means compared to the previous time window, if we're splitting our world as a sliding window of, let's say, aggregations of few seconds interval each. Okay, so we can discuss about how many of the flows in the current window are the same as the previous window, as the window before them, etc. And such kind of manipulations actually, as we showcased in this work, giving lots of information on the patterns in the underlying data in the network. And when accompanied with this approach, with this auto-encoder lossless normalization, are able to detect attacks very accurately, as I will show you. So this is the method. Okay, we have the data in this sliding window fashion. Each window is consisting of aggregations of some few seconds interval with the features similarly to the 2 examples I showed you before, the distribution of flows, new flows, etc. And this sliding window is fed into the autoencoder. The autoencoder itself is basically a vanilla autoencoder in its architecture. The key difference is, of course, what's coming after the autoencoder, the normalization, which is normalizing the loss from the different distribution, which is affected by the network type, the network size. Of course, smaller networks will have basically lower values of losses of the normal data compared to like more volatile networks with more changes among them. And this is being covered by the normalization that is added at the end after the autoencoder. And this normalized loss is then being forwarded to the global detector, which is able to to detect if there is anomaly or not. The normalization itself is actually being done by different normalization metrics. For example, we found that min-max is very good for one kind of our problems, and that normalization is very good for another one. And of course, there are more details in the paper that we published, and it's open for all. And regarding the features themselves, so I told you in the beginning about the two equivalent or very similar pipelines, right? The pipeline of the anomaly detection and the pipeline of the anomaly classification. I told you that both of them are based on similar approach, auto-encoder, normalization, and then either the global detector or the global classifier. And we found out that different features base and different normalization types are best suited for each one of these pipelines. So for example, the AEV1, which is the autoencoder for the first part, for the anomaly detection, we found out that using global features, which are mainly looking on general patterns of the data, very similarly to the examples I showed you before, like the distribution of new flows, distribution of same flows, distribution of flows themselves. These features were found out to be very good in detecting anomaly, in creating this high trade-off between accuracy and high accuracy and low false alarms. And afterwards, after the autoencoder 1 was detecting anomaly, we have the second pipeline, which is much more local, much more robust, much more descriptive, and its purpose is actually to provide us details about the anomaly. And in this pipeline, we use much more descriptive features, such as about the ports, the protocols, the top tokens, in order to give us better details on the anomaly that was detected. So the global model, which I told you, for example, feed-forward neural network, getting the normalized losses of different devices in the network, and using these normalized losses to detect anomaly or not. And this is the summary, combining everything all together with the inputs, the autoencoder, the normalization, and the global models. Okay, some simulation study. So the first thing we wanted to show is that the normalization is indeed effective, that it's able to transform us from raw different spaces to this domain invariant distribution. And we took different clients, 4 of our clients with the most varied behavior, one of the other, the size, the architecture. And we showed that we used the Kolmogorov-Smirnov, the KS test, to show that before normalization, the distributions are very different one from the other. And after the normalization, indeed, we are getting into the similar distribution. The KS stats are over 0.05, which means we cannot reject the null hypothesis, and it means that they have a similar statistical distribution. So it was a first demonstration of the similar distribution. Afterwards, we simulated this environment where we used data sets from the University of New Brunswick in Canada, and we took different data sets. It's a very good data set for this purpose, because each one of the data sets is very consists of a different network, different architecture, different behaviors. So it's a very good for our use case of showing this learning from different clients one to the other. And we also implemented Kitson, which is a recent state-of-the-art approach, which is based on the traditional autoencoders method. And we compared both of our approach and Kitson. You can see here it starts with like twice as good as precision, recall, and mainly F1 score, combining both together. of our approach compared to Kitson. Here in the left-hand side, you can see something which is very interesting, I think. This is the transfer learning in action. You can see that our normalized approach, being trained only on one data set, is of course providing better results than Kitson. But then when we add another data set, when we train our approach on two different data sets, it's actually improving the F1 score from 0.45 to 0.55. And this is what this is exactly what I told you before, how we utilize this knowledge from different networks, from different clients, from each new detection that we see, because of the normalization apple-to-apple consequences. And of course, more results that you can see. And another thing which is important to emphasize is that our approach, because of the sliding window fashion of it, is also able to predict threats before they hit. So in many cases, if we just analyze it from the recall, precision, metrics, it's a quite hard overestimation of the actual accuracy of our approach, because many of the detections are actually preceding the attack themselves, because of the analyzing of the patterns that preceding the attack or the threat itself. So the results, the accuracy is much better in reality than the results I showed you before. Okay, so I'm really close to the finish here. Adversarial attacks. This is becoming a very interesting topic. In the past, mainly pure academical discussion, but today's with the AI-based attacks, it's becoming very important to understand how much the solution is able to cope against such AI adversarial attacker. And I think that we clearly understand that sampling is one of the most significant built-in countermeasures that we can have against such an adversarial attacker, because of the randomness that is being added by definition to the solution, right? The attacker cannot know what packets will be sampled and what will not be sampled. And not only this, the attacker cannot know what is the raw loss and what is the normalization that was being used by our solution. So it has no idea in action about our model, and the adversarial robustness is very strong in such case. So I presented you this new concept of autoencoders, losses normalization, and transfer learning. The two steps, the normalization and then the forwarding to a global detection model and global classification model. And we discussed about the advantages of the sampling and the global approaches. And I went quite briefly on the simulations, but of course you can see full more details and also about the implementation in our paper. And before opening for questions, of course, we are hiring all different roles, specifically data scientists, ML developers, etc. And of course, you can feel free to reach out to me directly in this email about this or anything else. So thank you very much, and I'm open for any questions.
Why a smart detector can't just sit on the detector and analyze the network traffic patterns and align either text with the traffic pattern, so you won't see any major change in the global distribution?
So you mean in attack, you assume the attacker will be able to have full coverage of the entire network and manipulate it?
To sit on the traffic points that he wants to sit on, and analyze the traffic from these points and align his attack with the traffic points, so you won't see a massive change in the number of packets, or you will only send to Google when he knows that other will send things to Google, something like that. What prevents the global detector from how the global detector consider these things?
So the global detector is getting the normalized losses from different gateways in the network. So in order for adversarial attacker to have enough significant effect on the global detector, it needs to have a significant footprint in many of these key gateways in the network. So which is becoming equivalent to having manipulating the majority of the network. It's like I believe a very significant assumption.
Another related question: what if the detector only needs a very few steps in order to do something pretty significant?
Okay, so this is from a different question. So this is very good question actually, because the thing is that cyber attacks are not just a singular event. Okay, it's not just one packet out of the blue that is happening. It's actually a flow of different steps. Okay, you have the infection into the network, you have the penetration, you have the lateral movement, the propagation internally, you have this keep alives, you have the launch. It's a quite a process. So it's not just one packet that we sampled or not sampled. And in this process, because our approach is able to cover the entire network for the first time, we have much more places to intervene and predict the attack in the making actually, compared to existing approaches, of course, that becoming really a likelihood question that haven't the attack went through them, yes, no, etc.